Impossible. And therefore, if I had a potential which had a ground state like this and an excited state potential that looks like that, what happens? 0 can't go to 0. But what can it do? 1, 2, 3, 4. 0 can go to 4, vertical line, 0 kinetic energy, 0 kinetic energy, that's okay. It can therefore go from V equal to 0 to V equal to 4, but it can't go from V equal to 0 to maybe V equal to now 0 or V equal to 1, simply because it cannot keep the internuclear distance constant and it cannot keep the velocity constant if it made a jump from 0 to 0. And therefore, as per Frank's statement, which I have written over there, you have to ensure that any transition internuclear distance has to be the same just before and just after. Velocities have to be the same just before and just after. And if the transition violates even one of these, such a transition is not going to be possible. In this case, that's not possible. Yeah.
Say if we have a situation in which there is one other state, potential electron which is hurting at that point only, and that is also corresponding to 0 velocity. So which state will the electron refer to?
Here. I mean like this. So it can go from here to here, and this is, let us say, V equal to 4, and let's say this is V equal to 0. So essentially this can jump from here to here. It can therefore, in this case, can go to both V equal to 4, and it can go to the other state. The molecule can actually make a transition to both electronic states, provided the selection rules for going to this and this are both allowed. But to do the selection rules, we have to start studying term states, which we haven't done yet. But when you do that, we will see. But taking a question and putting the cart before the horse, if the electronic selection rules allows the molecule to go to this state and this state, and we saw that in that atom, right? S cannot go to D. Why? Delta L is not plus minus 1. So like that, you have selection rules for molecules too. So if this molecule cannot go to this state because of those rules, then this is not even in question. But supposing this state can actually make a transition to this as well as this, let's say both are allowed, then the Frank principle will then come and tell you that for a transition from here to here and here to here, for this state it can go from 0 to 4, and for this state it can go from 0 to 0 because it allows both of them. Okay, that will depend on the transition probabilities connecting this state and this state and this state and this state. The transition probability, as we saw earlier, is a little integral, which tells the probability of transition from one state to the other. If the transition probability from here to here is greater than from here to here, then most of the time it's making a transition to be equal to 4. If the transition probability is nearly equal, there's a 50-50 chance it will go to either this state or the other one. Okay?
Yeah, so just before this transition happens, are you assuming that that molecule was in the repulsive in the inner boundary?
Yeah. Good point. I didn't have to assume the molecule actually can absorb light on any one of these points. I'm just starting this argument from this point. But supposing this molecule, let me erase the state which she brought up so that we don't have the. Let's say we go from here and consider each one of these levels. It's a straight line, vertical line. Therefore, I don't have a problem with the first part of Frank's statement, which is the R must be conserved. But what about the potential energy, kinetic energy issue? The kinetic energy here is this much. For this state, it is this much. Seems larger than what I have over here. So if a molecule at this point will absorb energy, it will go to none of these states. But if it made a transition at this point, then of course it will go to this state. So depending on where it absorbs the light, it can actually go to any one of these states. But in the long run, at the end of the day, you have to integrate, meaning that going from here to here, the molecule can absorb light at any one of these points. When it absorbs from here, it can go here. When it absorbs from here, maybe, no, I don't have a curve. So essentially it means from this state, the major transition is going to come from molecules that are absorbing from here. Let me draw one more potential and answer your question better. Okay, and this will explain. If the molecule made a jump from here, 0, 1, 2, 3, what will it do? Allow, great. Vertical transition, 0 potential energy, 0 kinetic energy, 0 kinetic energy. So Planck's statement is obeyed in its entirety. Let me jump from here. Then what happens? From here, I can go from here to V equal to 0, meaning depending on where the molecule actually absorbs the light, it could go from V equal to 0 to V equal to 3 in one case, and V equal to 0 to V equal to 1 in another case, which means if you actually recorded a spectrum, you will see both transitions. Because the molecule can actually absorb light anywhere on the traverse, and therefore you will see this transition as well as this transition in the potential that I just drew for you. But you have done, I don't know that you have done the the harmonic oscillator wave functions. You have done particle box wave functions, right? And what do the wave functions tell you? It tells you where the probability is going to be the greatest. So if I had a particle in the box, which was something like this is my V equal to 0 function. Likewise, you can write wave functions for the vibration levels, and that will actually tell you, like in the first case, the vibration wave function is like this. What does that mean really? It means most of the time the molecule is spending time out here. And if from here it can't make a transition, what does that mean? The intensity is going to be very small. On the few occasions that it visits this place and visits this place, if it is lucky, it will make a transition. But most of the time it is actually spending its time right in the middle, and from the middle it doesn't seem like, oh, maybe I can. Let's say if I do this vertical, and this is the same as this, then what does it mean? I can actually make a transition from here to here. And because I'm spending a lot of time out here, so that's where the probability density is the greatest, that means the molecule can go from V0 to upper state V0, because it will obey the Planck's first statement, it will obey the Planck's second statement, and moreover, at the point when it is obeying these statements, it is actually spending a lot of time. And therefore, this transition will be quite strong. So you see therefore that the Planck statement actually gives you a very physical picture how the transition will actually be decided. It will be decided by two factors: conservation of position and conservation of kinetic energy. And if I conserve these two, just before and just after the transition, such a transition is going to be possible. The next question you have to ask yourself is, in all those places where the position is conserved and the kinetic energy is conserved, like in this place, what is the amount of time the molecule spends there? If it spends a lot of time, then of course, all factors are taken. At that point, any jump will cause it to have conserved position. Any jump will let it have conserved velocity, and it also spends a lot of time at this point. And therefore, this transition is actually going to be favored. The molecule will actually make a 0-0 transition quite strongly. In other words, we are not talking about selection rules now. We are actually talking about something called propensity rules. And what do I mean by a propensity? How probable is it for it to happen? In a selection rule, I am very strict. Delta K equals plus minus 1. You bring in plus minus 2, it's not going to happen. In this case, it's not that way. This to this is very probable. This to this is very less probable, less intense. And then, of course, this to something else is not even probable. Why? Because the Planck's first and the second statement are not even obeyed during this transition. So this is how Planck actually explained why in some states you see transitions going from 0, 0, 0, 0, 0 to 0, 0 to 1, 0 to 2, and so on, while some other transitions in some other molecule You don't see 0 to 0, you don't see 0 to 1, you see 0 to 10, 11, 12 and so on. When will that happen? Take the state. And put it out here. What does this mean? I'm going from bonding to anti-bonding. It's gone out. If you look at the rotation spectrum, who will form the head? R will form the head because it's gone out there. But what is the vibration spectrum? Can I ever go from V0 to this level? I can't go from here. I can't go from here either. In other words, such a location, you will never see a V0 to V0 transition. The best you might see is, and of course from here, there is nothing. Which means, from here you can never go to V0. Such a location. Yeah, we have a cricket game coming up. So such a location, you will not even see a V0 to V0. So in all those cases where people said, we are not seeing V0 to V0, but we are seeing 0 to 10, 0 to 11, 0 to 12, what is that immediately telling you? It's immediately telling you that the upper state potential is probably shifted out. And therefore, you are not even seeing 0-0 transition. Upper state potential is shifted out. What does the also tell you? R must form ahead. So you see that these things will all come together. You probably won't see 0-0, you want to see R head. You know that the upper state potential is way out. The upper state potential is way out. It simply means you have gone from bonding to anti-bonding. So all this information starts to surface the moment you look at this situation. And this propensity for transition, not a selection loop, a propensity loop, as starting from a given vibration level. Which vibration levels can you access in the excited state? Was actually told to us by Frank by using this very simple-minded dynamics issue. Electronic transitions are far too fast. Nuclear motion is far too slow. Well, that's the case. R has to be the same, velocity has to be the same, just before and just after the charge. And if that is the case, everything else follows. You can actually give intensities, or you can actually tell about which transition will be allowed and which transition will not be allowed by simply using the Frank statement. Frank statement was great. It almost, of course, it never gave us quantitative measurements of intensity, and we will see how to get that. All it said was this is possible, this is not possible. But it never actually told you how to calculate what the probability is going to be. Propensity is a probability issue. But it never told you of a way by which you can calculate these probabilities. All you can therefore say is in a very qualitative fashion, this transition I don't think will happen. This transition I think will happen. So it's more, non-quantitative. There was one problem with Frank, and therefore people never re-elected a whole lot. But then they had a more serious problem. Frank seemed to be completely shaking the very cornerstone of quantum mechanics. What's the cornerstone of quantum mechanics? The Heisenberg uncertainty principle. And what does the Heisenberg uncertainty principle tell you? You can't fix the position or fix and the momentum accurately simultaneously. So if you can tell me something very quantitative, very accurately about the position, you have no business to talk to me about momentum. And if you tell me that the momentum is something I know quite accurately, you have no business to talk to me about position. You know only one or the other. You can't know both at the same time accurately. And what was Frank doing here? He was saying position is not changing, velocity is not changing, but velocity is not changing, the momentum is not changing. The moment he said well, position is not changing, he had no business to speak about momentum. And the moment he said momentum is not changing, he had no business to talk about position. But that didn't bother Frank. He just went ahead and said all these things, which was actually shaking the very basis or the cornerstone of quantum mechanics, which is the Heisenberg principle of uncertainty. So while Frank's statement seemed to give us a good handle, actually his statement was quite good. Most experimental data could be explained on that basis. But we just couldn't accept it because it was hurting another very important issue in quantum chemistry, Heisenberg principle. And therefore we have to see if there is some way we can bring truths between Heisenberg and Frank, who now seem to be at loggerheads. So we have to do something to get truth between these two great spectroscopists and quantum mechanics people. And that is where quantum came in. Condon brought in the issues that quantum mechanics was happy. He took the issues which Frank was saying and he put the two together so that Frank's statement was now no longer a violation of quantum chemistry. And within the tenets of quantum chemistry, he was able to explain what Frank was trying to tell us. In other words, Condon gave us a very mechanical interpretation of Condon's statement. And once that was brought in, then there was no problem. Already 6 o'clock and now the time to discuss the Condon's interpretation. So we will do this on Friday. When we get back, we will start talking about the Condon's interpretation of Frank's statement and we will see how that is going to be accepted. Yeah.